A very good afternoon to all of you. Myself, Dr. Varun Narayan Misra, and today I am going to discuss about the unsupervised classification methods for urban area mapping. In the last class, we have discussed about the supervised classification methods, different types of processes that is involved in unsupervised classification methods, advantages and disadvantages of different supervised classification methods for mapping or monitoring the urban area. So today we will see a second type of classification, which is known as unsupervised classification methods, and how it work and what are the advantages and disadvantages of unsupervised classification method. So quickly, I would like to summarize the definition of digital image classification. As we know that multispectral classification is the process of sorting or grouping the pixels into a finite number of individual classes or categories. Okay, based on their data file. If a pixel is if a pixel satisfies a certain set of criteria, the pixel is assigned to the class that corresponds to that criteria. Multispectral classification may be performed using a variety of algorithms. The classification algorithms are of two types, basically hard classification or hybrid classification. In some of the cases, we also use fuzzy logic for classification purpose. The hard classification includes supervised or unsupervised classification approach. We have already discussed different types of supervised classification approaches. And right now, today, we will discuss about unsupervised classification approach. So digital image classification is basically the grouping of similar kind of pixels on the basis of their spectral response. It is very much useful for the separation of dissimilar objects and assigning the class a pixel, assigning the class label to a pixel. Okay, so automatic categorization of the pixels of the same type, and we assign a class label to that pixel. This process is known as digital image classification, and the result will be the manageable size of the classes. Initially, the pixels are in the form of digital numbers. When we categorize or when we group the pixels of same kind, then it is very easy to manage the size of the classes. Now, this is the entire classification process. We will start from the selection of image data. That is a kind of remote sensing data set. Then the second step, we will define or we will create different training data sets or training signatures. Okay, then after we will use training and selection of the algorithms, we will see or we will check which classification algorithm is suitable for the classification, which method is suitable for this classification. After that, we will define the clusters in the feature space. That will be done by running the actual classification. Then we will classify the data and we will get the desired result. And then there is a validation process of the classified results. That validation will be done on the basis of some testing data sets or on the basis of some ground data sets that is also acquired using remote sensing data sets or remote sensing images. So this is the entire process of image classification. So now we are going to start about the unsupervised classification. So as all we know that it requires only a minimum amount of the initial input from the analyst, and all the numerical operations are performed that search the natural groupings of the spectral properties of the pictures. Okay, so in unsupervised classification, there are certain statistical or certain numerical operations are there that is used for the natural groupings, that is used for the categorization of the pixels of the same spectral response or having same spectral properties. So the user allows computer or machine to select the class means and covariance matrices that can be used in the classification. Once the data are classified, then the analyst or user attempts a post priori to assign these natural classes to the information class of the interest. And if some clusters may be meaningless because they represent the mixed classes, then we avoid these classes of these kind of mixed pixels. And the clustering algorithms used for the unsupervised classification generally vary according to the efficiency with which the clustering takes place. So two commonly used methods for the clustering algorithms that is used in unsupervised classification is chain method and isodata clustering. Using chain method or isodata clustering, we can perform the clustering of the same kind of pixels that can be used for unsupervised classification. So now we will see first what is chain method. So in chain method, it is defined as a operation of two pass models. That you can say it passes through the registered multispectral data set two times. In the first pass, the program reads through the data set and subsequently builds the clusters, and a mean vector is associated with each cluster. While in the second pass, a minimum distance to mean classification algorithm is applied to whole dataset or to whole satellite image on a pixel by pixel basis, so that each pixel is assigned to one of the mean vector that is created in pass 1. So the first pass automatically creates the cluster signature that will be used by the unsupervised classification. So this is the entire process of chain method. The chain method operates in two modes. In first mode, it passes through the registered multispectral images, multispectral remote sensing images, and in the second phase, it uses minimum distance to mean classification algorithm and passes on pixel by pixel basis, whereas each pixel is assigned to one of the mean vector that is created in the pass 1. So this is about the chain method. Okay, so in detail we can see here the in pass 1, that is a cluster building process, in which during the first pass the analyst is required to supply four types of information. These four type of information is very important for building a cluster in pass 1 of the chain method. That first requirement is R, which is the radius distance in spectral space that is used to determine when a new cluster should be formed. Then C is the spectral space, that is distance parameter used when the merging clusters when n is reached. N is the number of pixels to be evaluated between each major merging classes of pixels, and Cmax is the maximum number of clusters that to be identified. So these four steps are involved in the cluster building, and in pass 2, the assignment of the pixels to one of the Cmax clusters using minimum distance classification logic. So the entire process includes two processes: the cluster building and assignment of a class to a certain clusters with a minimum distance to mean classification method. Okay, so this is the figure showing how we can perform the clustering of the pixels. That is a kind of, you can see here, it is a graph x and y coordinates of the pixel values between band 4 and band 5. You can see the pixel 1, pixel 2, pixel 3 having xy coordinates on the basis of the brightness value or dn values in band 4 and band 5. So originally the brightness value of pixel 1 and 2 or 3 as measured in the band 4 and band 5 of the hypothetical, or you can say the hyper multispectral remote sensing data sets. Okay, so now this is the distance d in the two-dimensional space, that is between pixel 1, which is a cluster 1, and pixel 2, which is a cluster 2, in the first iteration, that is computed and tested against the value of r is equal to 15, which is the minimum acceptable radius. Okay, this is the minimum acceptable radius for both the clusters, that is pixel 1 and pixel 2. In this case, d does not exceed r, therefore we can merge the cluster 1 and cluster 2 as shown in the next figure. Yeah, this is the way in which we can merge the pixel 1 pixel 2. Now pixel 1 and pixel 2 represent the cluster 1, and it is important to note that here the location of the cluster 1 has migrated from the pixel value 10 to 15 after the first iteration. Now it moves to the pixel 3. The distance, pixel 3 distance, that is d is equal to 15.81, is computed to see if it is greater than the minimum threshold, that is r is equal to 15. It is so the pixel location 3 becomes cluster 2. This process continues until all 20 clusters are identified, and then the 20 clusters are evaluated using a distance measure C to merge the clusters that are closest to one another. So this is the way in which we can perform the clustering. We can perform the clusters of the pixels, and we can repeat the process until it reaches or it covers the all 20 clusters, or all, you can say, the every clusters that is associated with the pixels. Okay, so now then in the next phase, the clusters that is migrated during the several iterations of the clustering algorithm, the final editing point represents the mean vector that would be used in phase 2 of the clustering process when the minimum distance classification is performed. So this is the way we can do the clustering, and then we can assign the pixels to the clusters. Okay, so it is important to note that as more points are added to a cluster, the mean shifts the less dramatically, since the new computed mean is weighted by the number of pixels which is currently in a cluster. So the ending point is the spectral location of the final mean vector that is used as a signature in minimum distance classification, which is applied in pass 2. In some of the clusters or in clustering algorithms, it also allows the analyst to initially seed the mean vector for several of the important classes. The seed data are usually obtained in a supervised fashion, as discussed previously. Others allow the analyst to use a priori information to direct the clustering process. So this is the way we can do the clustering. Okay, so in pass 2, now in pass 1 we perform the cluster, whereas in pass 2 or in second phase we assign the pixels to one of the Cmax clusters using the minimum distance classification algorithm. So the final cluster mean data vector are used in a minimum distance to means classification algorithm to classify all the pixels in the image onto one of the Cmax cluster. Now second type of process is ISO data clustering. We have discussed that chain method. Now second and important type of clustering method is ISO data clustering. So the full form of ISO data is iterative self-organizing data analyst technique. It represents a comprehensive heuristic procedures that have been incorporated into an iterative classification algorithm. Okay, in isodata clustering or in isodata algorithm, it is a kind of modification of the k-means clustering algorithm, which includes merging the clusters if their separation distance in multispectral feature space is below a user-defined threshold value, or you can say the rules for splitting a single cluster into two clusters. So isodata is a iterative process. It works, or it makes a large number of passes. It is a kind of iterative process, and it works as a large number of passes through the remote sensing dataset until it, it, it specified the results that are obtained instead of just two passes. Okay, in chain method, there are only two passes, pass 1 and pass 2. In pass 1, we perform the clustering, and in pass 2, we assign the classes. Whereas in isodata clustering, there are large number of classes. There are a large number of passes, or you can say the it is an iterative process. It is having multiple iterations until the specified results are obtained. So isodata does not allocate its initial mean vector, which was based on the analysis of pixels. Rather, it is an initial arbitrary assignment of all the Cmax clusters that can take place along an n-dimensional vector that runs between the specific points of the feature space. So isodata clustering is having advantages over the chain method. It is having multiple iterations. It is the advantages of having multiple times processing of the same pixels, so that it can provide us the accurate data. It can provide us the most precise clustering of the pixels of the same type. Okay, so in isodata algorithm or isodata clustering method, generally the analyst needs to specify the Cmax, that is the maximum number of clusters that to be identified, or T is equal to maximum percentage of the pixels whose class values are allowed to be unchanged between the iterations. M is the maximum number of times the isodata is to classify the pixels and recalculate the cluster mean vectors. So the minimum members in a cluster or maximum standard deviation for a cluster. Split separation value. If the value is changed from 0, it takes the place of standard deviation. The minimum distance between cluster means are considered in the isodata clustering algorithm. Okay, in isodata clustering algorithm, that is a phase 1, we can build the clusters that using many phases through the data set. So in the clustering process, the isodata initially distributes the 5 hypothetical mean vectors using plus minus 1 standard deviation in both the beginning and the ending point. And in the first iteration, each candidate pixel is compared, or it is used to compare for each cluster mean that assign to the cluster whose mean is closest in the Euclidean distance. During the second iteration, a new mean is calculated for each cluster that is based on the actual spectral location of the pixels that is assigned to the each cluster instead of initial arbitrary calculation. And the split merge assign the process that continues until there is little change in the class assignment between the iterations. The t threshold is reached or the maximum number of iteration is reached, that is m. So it repeats the process or iteration. It repeats multiple iterations until the maximum number of iterations is reached or the threshold value is reached, that is t, or maximum number of iterations, that is m. Okay, so this is the way in which we can see that how this isodata clustering builds the clusters. So in figure A, you can see the distribution of 20 isodata means vector are just one iteration, whereas the distribution of 20 isodata mean vectors after 20 iterations, the bulk of the important feature space, that is a gray background, is partitioned rather well after 20 iterations. So you can see the difference between the 20 isodata mean vectors or the distribution of 20 isodata mean vectors after 20 iterations. So it is very important to see the maximum number of iterations provide you the more informative clusters or provide you the most precise clusters of the pixels, so that it may be useful for unsupervised classification of the satellite images. Okay, so there are also the certain you can say the uncertainty is there. Maybe the sources of uncertainty in image classification, that the non-representative training areas, high variability in the spectral signature for land cover classes or mixed land cover classes within the pixel area. These three are the sources of uncertainties. Means when we perform supervised or unsupervised classification, whatever the classification method we are going to use, these are the sources of uncertainties. The results are affected by these of the factors. The first one is that the non-representative training areas. Okay, then second is very important, high variability in the spectral signature of the land cover classes. If the study area is having the classes which is very high variability in the spectral response, so it may affect the classification results, it may affect the classification accuracy. Or in third source is that the mixed land cover within the pixel area. It is there is a possibility that a same pixel is having multiple classes, a same pixel having the reflectance that contributes to the mixed land cover classes. So these are some of the sources of uncertainties that definitely affects the classification procedure or classification results or accuracy of your classified data. Now moving to the next slide. So how to evaluate the classification? Okay, so after a classification process, these methods are available for testing the accuracy of the classification. When we perform the classification, when we get the classified result, so in the next step we evaluate our classification results. So these are two methods that are available for evaluating the classification method. First one is thresholding, and in thresholding we use a probability image file to screen out misclassified pixels. And second one is accuracy assessment, that compares the classification or classified results to the ground data or any other kind of data sources. Now accuracy assessment is very important when we perform classification or when we derive any land cover data set or any classified product. So we need to assess the accuracy of the classified results. So accuracy assessment in general is used for comparing the classification to the geographical data sets that are assumed to be true. Okay, in order to determine the accuracy of the classification process, generally the assumed the true data are derived from the ground truth data. So in accuracy assessment, we compare the classified result with the ground data, that is also known as ground truth data, which was derived or which was collected from the ground. Then we compare the classified data with the ground data to see the or to accurate or to assess the accuracy of our results. Okay, so accuracy assessment or the assessment of the accuracy of the classified products based on the remote sensing images is one of the most important steps in classification process. Without an accuracy assessment, the output or results is of little value. We need to validate our classification results. We need to validate our classified product. Without this, it will not be of great significance. It will not be used for any further application or any further analysis. So, in accuracy assessment, there are a number of issues that are relevant to the generalization or the assessment of the errors in the classification. Okay, these include the nature of the classification, sample design, or assessment sample size. Okay, so whatever the classification method we are using, or what kind of classification process you applied on the satellite images to get the classified product, it also affects the classification, or you can say the accuracy assessment of classification. What was the sample size? What was the sample size for the assessment? These are some factors that are responsible for the assessment, or you can say these are the factors that directly or indirectly affects the assessment of the errors in classified product or in classified data sets. Okay, so first is that nature of classification. So what kind of classification we are dealing with, and what kind of classification methods we are using. So the nature of classification includes the class definition problems. It occurs when we try to extract the information from the image, such as tree height, which is unrealistic. If this happens, the error rate will increase. The first, we need to define the classes. The class definition is an important step when we are going to perform the classification. Okay, during the image interpretation, or after analyzing the image, the class definition or the definition of the classes may be problematic while we are trying to extract the information from the satellite images. Okay, so if this happens, the error rate will increase. uh, most One of the most commonly used or one of the most commonly arise problem in classifying the remotely sensed data is to use the inappropriate class labels. Okay, you have to use the appropriate class labels, such as cliff, lake, or river, all of which are landforms and that are not land cover. Similarly, a common error is that of using class labels which define the land uses. These features are commonly made up of several land cover classes. So first, we need to define the classes. Class definition is important. Then we need to use the appropriate class labels. We need to provide appropriate name to the individual classes. These features are most commonly made up of several land cover classes. Third and the final point is here that in terms of the potential for the generation of error is the mislabeling of the classes. When we mislabel the classes, the most obvious example of this is to label a training site water when in fact it's something else. So we need to we do not need to mislabel the classes. If that the pixel is of water bodies, if the pixel is of fallow land or vegetation, we need to assign the accurate label of the classes. So this will result in at best a skewing of your classification statistics if your training site samples are sufficiently large, or at what worst shifting the training statistics entirely if your sites are relatively small. So the nature of classification includes the class definition problem. A common problem is inappropriate class labels, and the third and very important is mislabeling of the classes. Okay, these factors affect the classification results. Sample design is also having important role in the accuracy assessment. In addition to being independent of the original sample site, the sample used must be of design that will ensure the consistency and objectivity. Number of sampling techniques can be used. There are several sampling techniques are available. You need to define the samples on the basis of some sampling technique. Either you can use random sampling or systematic sampling or stratified random sampling technique. We need to perform the sampling on the basis of some of the available methods of the sampling, that is random sampling, systematic sampling, and stratified random sampling. Of the three, the most important and most widely used method is systematic sampling method. Okay, when we use the systematic sampling method, this approach results in a sample distribution which favors a particular class, that is depend on the distribution of the classes within the map. Okay, so only random sample designs can guarantee an unbiased sample. And when in case of the true random sampling strategy, however, may not yield a sample design that covers the entire map area, and so may be less than the ideal. In many instances, in many cases, it is found that the stratified random sampling strategy is the most useful tool, and in this case the map area is stratified based on either a systematic breakdown followed by a random sample design in each of the systematic subareas, or alternatively we can say through the application of a random sample within each of the map classes. The use of this approach will ensure that one has an adequate cover for the entire map, as well as generating a sufficient number of samples for each of the classes on the map. So sample designing or designing of the training samples is an important part of the accuracy assessment. Now moving to the next slide. Sample size is another important factor during accuracy assessment. The size of the samples which was used must be sufficiently large to the statistically representative of the study area. Okay, the number of points which is considered necessary varies depending on the method that is used to estimate. What this means is that when we use a systematic or random sample size, the number of points are kept to the manageable number, because the number of points that is contained within the stratified area is usually high, that is greater than the 10,000, which is the number of the samples which is used to test the accuracy of the classes through a stratified random sample, which will be high as well, as so that the cost for using a highly accurate sampling strategy is a large number of samples. Sample size should be the representative of the study area. Sample size should be the representative of the uh, statistical information of the pixels, so that it can be used for the classification and accuracy assessment of the satellite images. So error matrix is a method for the accuracy assessment. Once a classification is done, after the classification, we need to have the sampled contingency table, which is also referred as the error matrix or confusion matrix. Okay, so confusion matrix is a type of table which is used to properly analyze the validity of each class as well as the classification as a whole. In this way, we can evaluate in more detail the efficacy of the classification. So error matrix is a approach. Error matrix is a method to assess the accuracy. It is also considered. It is also known as error matrix or confusion matrix or contingency table. Okay, so this is the best way to evaluate the efficacy of the classification or the accuracy of the classification results of classified maps. Okay, so one way to assess the accuracy is to go out in the field and observe the actual land classes, that is a ground truth data sets at a sample of the location, and compare it with the classified product, classified result. So there are a number of ways to quantitatively express the amount of the agreement between ground truth classes and the remote sensing classes. Okay, so there should be good agreement between the ground truth classes and the remote sensing classes, which was obtained after the classification. And this can be done, this agreement can be expressed in a quantitative manner. These agreement can be expressed quantitatively. One of the best way to construct a confusion matrix approach is alternatively are known as the error matrix. Okay, so this is a row by column table which with as many rows are columns. So each row of the table is reserved for one of the information or remote sensing classes used by the classification algorithm, whereas the column displays the corresponding ground truth class in the identical order. So this is the table showing the number of you can say the pixels for classified data set and ground truth classes, that is ground truth information. So all entire information is arranged in the rows and column. Row represents the remote sensing classes and column represents the corresponding ground truth information or the actual class present on the ground, which is collected through the ground survey or ground sampling. Okay, now moving to the next slide. So okay, So on the basis of the table, we can assess or we can calculate the overall accuracy. So the diagonal elements tally the number of pixels classified correctly in each class. So an overall measure of the classification accuracy is calculated as the total number of corrected classification divided by the total number of classification. So which is in this sample amount to 35 plus 37 plus 51 divided by 136 is equal to 83%. But just because 83% classification was accurate overall does not mean that each category was successfully classified at that rate. Okay, so overall accuracy doesn't provide you the accurate information about the class wise accuracy, or it doesn't provide you the information how each category is classified at what level, and what is the successful classification, what is the accuracy rate of the classification of individual categories. So this overall accuracy only tells you the overall classification accuracy, which is dependent on the total number of correctly classified pixels divided by the total number of pixels which was considered during the classification and accuracy assessment. Now another measures for the accuracy assessment are users accuracy. Okay, so users accuracy is a kind of accuracy of the imagery who is particularly interested in a class A. When we want to assess the accuracy of a particular class or individual class, this is known as users accuracy. It might wish to know what proportion of the pixels assigned to class A were correctly assigned. In this example, you can see here the 35 of the 39 pixels were correctly assigned to the class A. So at the end we can calculate the user's accuracy for such that class is that 35 divided by 39, which is 90%. Okay, this is the way we can assess or we can calculate the user's accuracy for the classified map for individual class or for a specific class. Okay, in general the particular category is user accuracy, which is computed by using the formula the total number of correctly classified pixels divided by the total number of classification in the category, which for an error matrix setup with the row and column assignments, as stated, that number of diagonal cell of the error matrix divided by total number of pixels in a row. Okay, so evidently a user accuracy can be computed for each row. So if there are multiple classes, there are multiple categories for a classified data set, so we can calculate the user's accuracy for individual category, for individual class. So it will provide you the accuracy of the successful classification of individual class for that satellite image. Okay, producer's accuracy contrasted to the user's accuracy is the accuracy measure which has a slight different interpretation. Producer's accuracy is a measure of how much of the land in each category was classified correctly. It is found that for each class or category as the number of diagonal cells of the error matrix divided by the number of column total. So here you can see the producer's accuracy for class A is 35 divided by 50, which is 70%. So producer's accuracy tells us the accuracy of the class, or you can say it is the measure of how much a land use category or how much a landscape category in was classified correctly. So it can be calculated by dividing the number of pixels in that class and total number of ground truth pixels. And in this example, you can see it can be calculated as 35 divided by 50, or we are getting the result of 70%. So from this assessment, we have the three measures of the accuracy. We have the three kinds of accuracy measures. That is overall accuracy that takes no account of the source of error, that is error of emission or error of commission. User's accuracy measures the proportion of each class which is correct, and producer's accuracy provides us the proportion of the land base which is correctly classified. So these three accuracy measures are used for assessing the accuracy of classified maps: overall accuracy, user's accuracy, and producer's accuracy. Another type of accuracy measure is kappa coefficient. So it is another measure of the accuracy of the classified map, which is a measure of the proportion or percentage improvement by the classification over a purely random assignment to the class. So for an error matrix or confusion matrix with r number of rows and hence the some number of columns. Let a the sum of the diagonal elements, which is the number or which is the numerator in the computational of the overall accuracy. Then the kappa coefficient can be calculated using the formula k is equal to na minus b upon n square minus b, where n is the total number of pixels in the error matrix and the sum of all r individual cell values. This is the kappa coefficient. This is the way we can calculate the kappa coefficient. For the above error matrix, for the class A, B, and C, we can easily calculate the kappa coefficient. Kappa coefficient provides us the overall assessment of the accuracy of the map. It can be measured, it can be tested statistically by using the formula. Okay, this is the way using this table, using the value of the value of this table, we can easily calculate the kappa coefficient by applying the formula of na minus b upon n square minus b. Now, fuzzy classification is also a type of classification. This is the advanced classification method that takes into account that the pixels of the mixed classes, that is a pixel, cannot be definitely assigned to one category. So fuzzy classification is designed, it is used to help you with the data that may not fall into the exactly one category or another. Fuzzy classification works using a membership function, whereas a pixel's value is determined by whether it is closer to one class than another. Like the traditional classification method, the fuzzy classification still uses the training, but the biggest difference is that it is also possible to obtain information on the various constituent classes that is found in a mixed pixel. Fuzzy classification works well when there is a confusion of the pixels, or you can say the mixed type of pixels are there. So this is the way we can perform the fuzzy classification. This figure or this diagram is showing the diagrammatic representation of the working principle of the fuzzy classification. So the source for this figure is Hill 1997, the representation of the categorical ambiguity. Okay, so this is the way this figure is showing how fuzzy classification works and how it overcome the problem of mixing of the pixels, so that we can get the accurate classification results or accurate classified product. Okay, now moving to the next slide. Expert classification. Expert classification is another type of classification process in which the rule-based approach is applied to the multispectral image classification, that is post-classification refinement and the GIS modeling. In essence, an expert classification system is a hierarchy of the rules or a decision tree that describes the conditions under which a set of low-level constituent information gets abstracted into a set of high-level information classes. Expert classification is based on some kind of rules. Okay, we apply or we use some kind of rules, or you can say it's a kind of decision tree classification process in which we define some rules or threshold values that can be used for the classification of multispectral images. Okay, and it is an expert classification system. It works as a hierarchy of the rules or decision tree. So expert classification method can also be known as decision tree classification method. It describes, or we have to describe the condition under which a set of low level constituent information gets abstracted into a set of high level information classes. So this is the way we can perform the classification by assigning some threshold, or by assigning or by describing the condition by the user, so that the entire pixels in the multispectral images or the multispectral images will be classified into the desired number of classes. Okay, so it provides us the high level of information because we know the number of classes, what is the requirement of the classification, and we define the rule, we define some threshold values, and on the basis of that threshold value it provides us the classified product or classified output. Okay, these are the components of a typically analyzed or typically used rule-based expert system. In the rule-based expert system, we should have some user interface in the form of computers or laptops. Okay, in that we have some interface engine. The interface engine is a kind of method in which we solve the problem by drawing some conclusions, by which is based on the expert knowledge. Like if we are having the prior knowledge about the study area, if we know the prior reflectance pattern or prior information spectral response pattern of the classes, which is known as the expert knowledge. So expert is the knowledge base, that is a domain knowledge based on some hypothesis. We need to apply some hypothesis, we need to apply some rules, we need to define some conditions. So hypothesis, rule, and conditions, these are the domain knowledge. That's why it is known as expert knowledge. And by applying these expert knowledge, we can solve the problem by drawing some conclusion. Then it will be used for some other applications by different users. And we can also adopt it as a online database by uploading it on the server. So the components of a rule-based expert system includes a user interface, a user, then there may be some interface engine, there may be some expert knowledge on the basis of various kinds of hypotheses, the rules and conditions. And also we can have online databases, so you can say it's kind of web-based services. And we may have different kinds of applications by applying such kind of rule-based expert systems for the classification of multispectral satellite images. So this is the way. In today's lecture, we have discussed different types of unsupervised classification methods, how it works, what are the advantages and disadvantages of unsupervised classification methods, expert system classification method, fuzzy logic classification system, and accuracy assessment of the classified products, how we can assess the accuracy of the classified product so that it can be used for further applications. So this is all about the unsupervised classification methods that can be used for the mapping of urban area, or you can say it is used for mapping of the landscape into various land use land cover classes. And we can also assess the accuracy after applying the classification method, so that the information about the study area, either in terms of urban or non-urban area, it will be used for further planning, further mapping activities, or further any kind of sustainable development of that urban area. Thank you very much for today's class. Now we will meet again in the next class with next lecture. Thank you very much.